Welcome to electrical engineering. You're probably comfortable with linear systems by now, those predictable sequences where values step up by adding a constant number every time. But what happens when a system scales by a constant multiplier instead? Look at this progression. We go from 1 up to 5 to 25, 125, and suddenly we're at 625. In just 5 steps, a single unit has exploded into a massive cluster. The scale completely detaches from the starting point. If you need to know the state of this system at the 10th or 50th stage, calculating each step by hand is a waste of time. We need a precise mathematical language to predict these constant multipliers. We need geometric progression. A geometric progression is a sequence where every term after the first is found by multiplying the previous term by a fixed, non-zero constant. To map this out, we start by isolating the point of origin. In math, we call this the first term, represented by the letter A. Next, we identify that fixed multiplier. This is the common ratio, or R. You can find R at any point in the chain simply by dividing one term by the term that directly precedes it. It doesn't matter how aggressive the growth curve is. If you have A and R, you have the complete blueprint for the entire system. Let's test this framework on a sequence that oscillates between positive and negative values: 6, -12, 24, -48, 96. We start at the beginning. Our first term, A, is 6. To find our ratio, we divide the second term by the first term. -12 divided by 6 gives us a multiplier of -2. We can verify this further down the chain. 24 divided by -12 still equals -2. The constant holds. A negative multiplier forces the system's output polarity to flip at every step. But structurally, it remains a perfect geometric progression, which brings us to the ultimate shortcut, the general term formula. Notice the exponent is n-1. That's because the sequence's very first term is the starting line. It doesn't get hit by the multiplier until step 2. Let's use this to calculate the 10th term of a decaying sequence that starts at 9, drops to 3, then 1. Our A is 9, and since 3 divided by 9 is 1/3, our R is a fraction. We plug these variables in, raising 1/3 to the power of 10-1, which gives us 9 times 1/3 to the 9th power. This resolves out exactly to 1/2187. By relying on this formula, we bypass the manual arithmetic. We can instantly predict the exact state of a scaling system at any point in time. This graphic shows how these concepts appear on an actual evaluation. We're looking at part 2 of this problem, which asks for the 10th term of the sequence starting with 2, 6, 18, and 54. In electrical engineering, you can think of this exactly like a cascading amplifier circuit. The first term, our 2, is the initial input signal. The common ratio of 3 represents the amplifier's gain factor, boosting the signal at every stage. Calculating that 10th stage ensures that unchecked exponential signal gain doesn't overload and fry the physical hardware. This exact same multiplicative framework governs completely different fields too, like modeling the rapid daily replication rates of a bacterial colony. Whether you are tracking physical biology or electrical signals, the anatomy of the sequence is identical. Complex, sprawling systems, no matter how massively they scale over time, all resolve back into a single point of origin. For an electrical engineer, mastering the mathematical multiplier is the first step to mastering the entire physical system.